Hello everyone, I'm Austyn Oubre, and today I'm going to be talking to y'all about the Atkinson cycle. So to give a brief history about it, the cycle was named after the British engineer James Atkinson, pictured on the right. He was born in 1846 in Hampstead, London, and died in 1914, and his Atkinson cycle engine was patented in 1882. So some applications for the Atkinson cycle. The main use in today's world is in gas and electric hybrid vehicles. It's used because it has an advantage in higher efficiency than achievable in any auto engines. And this is ideal for hybrids because the electric motor makes up for the low speed output. And this is it's an improvement on the auto cycle because of that higher efficiency. So in these next few slides, we're going to have two images. And on the left is an auto cycle, the right is the Atkinson. So during the compression stroke, this is where it differs from the auto cycle. As you can see, the intake valve, it stays open for about 20 to 30% of the piston's upward travel. And since these are used in 4-cylinder engines, we know that one of the cylinders is in the intake stroke, which, because this compression stroke, the intake valve is open, it pushes that air and fuel back into the intake manifold, which in turn creates less losses. Next one. So during the power stroke, the payoff of the Atkinson cycle is after ignition, when the piston begins the power stroke. The full length expansion with short intake stroke gets more work per unit of fuel. So since there was less fuel being compressed, whenever it expands, it's less pressure, and that's what makes the expansion ratio bigger than what an auto cycle expansion ratio would be. So this is the exhaust stroke. As you can see, there's no difference between the Atkinson and the auto cycle. They're very similar. So these are the PV and TS diagrams of the Atkinson cycle. We have two isentropic processes, two constant volume processes, and a constant pressure process within the cycle and within the stroke. So this is a list of equations that gets us to our efficiency. So at first we start off with QR, where is equal to mCp delta T, and then Qs equal to mCv delta T. And this keeps on simplifying until we have our final efficiency equation, where it's 1 minus gamma, which is just a ratio of Cp to Cv, times E minus R over E to the power gamma minus R to the power gamma. And E and R, E is our expansion ratio, which is the volume of the exhaust stroke over the power stroke. And then R is our compression ratio, which is the volume of our intake stroke over our compression stroke. And since the expansion ratio is bigger in the Atkinson cycle, it creates, that's what makes the efficiency better when in comparison to the auto cycle. So in conclusion, although the Atkinson cycle does give you lower torque and lower power than the auto cycle, it does give you higher efficiency, which is why these are used with the hybrid vehicles. And another thing interesting is if you add a supercharger to the Atkinson cycle, that's what makes the Miller cycle. So are there any questions?